If you take a look at chapter 22, let me get there. It's measuring employment and unemployment, and it talks about some of the ways that people collect data, and we're going to skip the whole chapter. So moving on to 23, the accuracies of averages. So Lyndon B. Johnson said, ranges are for cattle. Oh, how funny. So page 409. Aubrey, do you want to start reading? Okay, so I'm recording this video for Hallie, and I just realized she can't hear you. So in that first paragraph, it says, how much chance variability is there in the average of numbers drawn from the box 1 through 7? So if I build a box, we can predict what's going to happen to the sum of the box or the average of the box. We can create an expected value. We can create a standard error. So we're going to go into that a little bit more because eventually we want to get rid of the box. So the computer program says make 25 draws at random with replacement from the box. And then they've done that. So there are 5 sets of 5 numbers. The sum of these numbers is 105, so the average is 4.2. The computer did the experiment again and again, and the results came out differently. So for the second set, the sum is 95, so that the average is 3.8. The sum of the draws is subject to chance variability, therefore the average is 2. The new problem is to calculate the expected value and standard error for the average of the draws. So far, we've only been doing the sum of the draws. So if I go into my stat and I put this list in, so 1, 2, 3, 4, 5, 6, and 7, and I accidentally put 34. So put a 4 there, and then we'll change this one to a 3. And then I do my one variable statistics, and I get the sum of the box is 28, the average of the box is 4, and the SD of the box is 2. And what we did in the past was, if I make 25 draws, what is expected to happen? Well, if my D is 25, then I just multiply that, and my expected value is 100 plus or minus. Do you remember how we did that? We took the standard deviation. So if you look over there, the SE for the number is the standard deviation of the box times the square root of the draws. So I times this by 5, and I get 10. That's for the sum. So everybody who plays this game 25 times is expected to earn 100 points plus or minus 10. And 68% of the people should land in that window. 95% of the people should be from 80 to 120. Okay, that's for the sum. What about for the average? Well, when the computer did a simulation, it ended up with an average of 4.2, and then it did it again, and it got another average, so average number 2 was 3.8. Can we create what the expected average is going to be and how far off it's going to be? Well, What is the expected average? 4. Why? Well, no. So it just so happens that the average of those is 4, but that's a total fluke. The average of the box is 4. So that is my best guess for the average. Does that make sense? Okay. So turn the page. So the average of the draws will be around blank, give or take blank or so. Okay, so the solution, the average of the box is 4. So the average of the draws will be around 4, give or take. The give or take number is the SE. To get the SE for the average, we go back to the sum. The expected value for the sum is 100, which I've written up there. The SD of the box is 2, and the SE for the sum is 10. So the sum will be around 100, give or take 10 or so, which is what I have. What does this say about the average of the draws? If the sum is 1 SE above the expected value, the average of the draws is, of the 25 draws, is 100 divided by 25 plus 10 divided by 25. So the average is essentially the sum divided by the draws. So this is my expected sum, and this is my expected standard error. So to calculate the average, I just need to divide this by 25, and I get 4, which happens to be that number, which we already knew, plus or minus this divided by 4, which is 2.5. Or not 4, sorry. How about we divide that by 25? That'll make way more sense. So 10 divided by 25 is 0.4. Does that make sense? We've never done this before, but it's essentially what we've been doing over and over and over. Okay. On the other hand, oh, nope, next one. The average of the draws will be about 4, give or take 0.4 or so. The 4 is the expected value for the average of the draws, which is essentially the expected value divided by the number of draws. The 0.4 is the standard error, completing the solution. The idea in brief, if the sum of 25 draws is 100 plus or minus 10, the average of 25 draws would be 100 over 25 plus or minus 10 over 25 or so. In other words, to find the SE for the average of the draws, just go back and get the SE for the sum, then divide by the number of draws. So we could have saved ourselves a ton of time if, let's get all this stuff out of the way. So we could have said that my expected average, my expected value for average is going to be 4 plus or minus, well, it's going to be the SE for number divided by the number of draws. So in this case, it's 2 times the square root of 25 divided by 25. That looks really familiar. That is exactly the same as the SEP. So the SE for average and the SE for percentage end up being the exact same equation. Okay? Now, we've simplified the SEP. We don't do it this way. What have we decided to do? We just take 2 and we divide it by the square root of 25. The reason is the square root of 25 over 25 is equivalent to the square root of 25 over the square root of 25 times the square root of 25. Right? This is just the square root of 25 times itself. Well, when you write it that way, those cancel, and I'm just left with 1 over the square root of 25. So when we do these calculations, we do it the easy way. and we say 2 divided by the square root of 25. It's not 2, is it? Yeah, it is. And I get 0.4. So the beauty of it is we already know how to compute the SE average. It's exactly the same as the SEP. Okay. Now, how is this box different? Well, when you're doing SEP, what sort of numbers are in the box? Not decimals. Well, okay. So percentage, but what are on the tickets? What numbers are on the tickets? 1 and 0. And then we just put the percentage of the decimal equivalent to the percentage for each group of 1s or 0s. And eventually we just stop putting 1s or 0s in there and we just put the percentages in there. So for an average box, the tickets have the actual value on them, which means we have to do our stat in order to calculate the average and the SD. With percentages, the average is given to us, and the SD is calculated using the SD shortcut. But when you're doing a sum or an average box, you can't do a shortcut. How come? Why is there no SD shortcut to this box? Right, the SD shortcut only works if there are 2 different tickets in the box. And this one has 7 different tickets. Okay. All right. So in the box on the bottom of page 410, when drawing at random from a box, the EV for average of draws is simply the average of the box, which you get doing one variable statistics. And the SE for the average of draws is the SE for sum divided by the number of draws. We don't do that. We actually just do the SD of the box divided by the square root of the draws because it's simpler. So the SE for the average says how far the average of the draws is likely to be from the average of the box. So I would expect 68% of the people who play this game to be between what 2 values? 3.6 and 4.4. Is that a confidence interval? Am I 68% confident? No, this is a probability. There is a chance. It hasn't happened yet. So there is a 68% probability that you will land inside that window when you make 25 draws from the box. So if I jump up to 95%, it would be 3.2 to 4.8. And again, that is not a confidence interval. That is a probability. Yes, pretty much. Exactly. Yep. Good point. So she asked, is this all the same from what we've done since chapter 5? And the answer is yes. We're just doing averages now. But this particular game is not very useful. You're not a casino. You don't want to know the chance of winning or losing. What we want to do is calculate the average when we don't know certain information. Okay, so at the top of page 411, the top panel shows a probability histogram for the sum of 25 draws from the box 1 through 7. The bottom panel shows the probability histogram for the average of the draws. What do you notice? They're exactly the same, which makes sense because what is the difference between 100 plus or minus 10? So what's the difference between this and this? All we did was divide everything by 25. So you'll notice the top panel goes from 70 to 130 with an average of 100. The bottom panel goes from 2.8 to 5.2 with an average of 4. The only difference is the bottom has been divided by 25. Okay. If the number of draws is large enough, the normal curve can be used to figure chances for the average. Figure 1 shows the probability histogram for the average of 25 draws from the box. The histogram follows the curve, so areas under the histogram can be approximated by areas underneath the curve. Why does the probability histogram for the average look like the normal curve? Because all we had to do was divide by 25. Okay, turn the page. When drawing at random from a box, the probability histogram for the average of the draws follows the normal curve, even if the contents of the box do not. The histogram must be put into standard units and the number of draws must be reasonably large. So it showed us a normal curve. Is this box normally distributed? Does it have a lot in the middle and less on the edges? No, the histogram for that looks like this. It's all the same level all the way across. Okay, but if we do enough draws, then the sum and the average will be normal. And it turns out the less normal the box is, the more draws it takes for the probability histogram or the histogram to turn into a normal curve. If the box is normal, then the draws will be normal really quickly. If the box is not normal, it takes more draws. Okay, so as long as you do enough draws, it will work. Okay, example 2. 100 draws will be made at random with replacement from the box in example 1. So it's the same 1 through 7. Maybe I shouldn't have erased the whole thing, huh? Because I'm still going to use a lot of this stuff. All right. So now my draws are equal to 100. What is my expected value for the average? Is that what it wants? Yep, average. It's going to be 4. Wait a minute, it was 4 last time. This is an average, right? If you do 10 draws, what's the average supposed to be? 4. If you do 100 draws, what's it supposed to be? 4. If you do 1,000,000 draws, 4. The sum goes up, but the average doesn't. Plus or minus. Last time it was 0.4. Before we do the calculation, do we expect the SE for averages to be greater or smaller with 100 draws? Last time when I did 25 draws, the SE average was 0.4. Do I expect this SE average to be bigger or smaller than 0.4? Well, what happens to a confidence interval when you do more draws? It gets smaller. This is not a confidence interval, but the same logic applies. Your error goes down when you make more draws. Well, your percent error goes down. So we're going to take 2 and divide it by the square root of 100. So 2 divided by 10 is plus or minus 0.2. So now I am more likely to be closer to 4 with 100 draws than I would have been with 25 draws. And it turns out the more draws you make, the smaller that SE is going to be. Okay. B, estimate the chance that the average of the draws will be more than 4.2. So I draw my normal curve. 4 is in the middle, plus or minus 0.2. So I want to know from 4.2 this way, what is the area? Well, I can do that in my head. Anybody else? How do I do that in my head? So the middle area would be 68, because I'm 1 SE. So this is 68, which means the edges must be 32. But I'm only doing 1/2 of that, so about 16%. Okay? If you didn't know how to do that, then you would do 4.2 minus 4, divide that by 0.2, and we would get 1, and we would shade norm from 1 to 5. And according to the book, you get, I saw it's about 16%. Okay, any questions there? All right, in example 1 and 2, when the number of draws went up by a factor of 4, from 25 to 100, the SE for the average of the draws went down by a factor of 2. Okay, and you should have known this from something we've learned before. So in general, when drawing at random with replacement from a box of tickets, multiplying the number of draws by a factor of 4 divides the SE for the average of the draws by the square root of the factor. Now, you didn't understand what that meant. So, let's say I have 100 draws. And my sum, and I'm just making this up, let's say my sum is 500 plus or minus 50. Okay? My average is going to be 5 plus or minus 1/2. Does everybody get that? Okay. Well, what if I switch and I do 900 draws? Well, this is going to be 9 times as big. So 500 times 9 is 4,500. Plus or minus, what happens here? Does this get 900 times bigger? No, because the more draws we make, the higher my error, but the smaller my percent error. We've talked about this a lot, and now you actually get to see it in motion. So if this goes up by 9, this goes up by the square root of 9. So this turns into 150. Why is that significant? Well, you are more likely, the more draws you do, the further you're expected to be from the actual value. But the smaller this is going to be in comparison to that. So if you do 100 draws, then you might be $50 away from the total, right? If you do 900 draws, you might be $150 away, which is bigger. But when we compare those, 50 divided by 1,000 is an error of, I might be off by 5%. But if I do 900 draws, 150, oh wait, I did that wrong, didn't I? It should be 100. Sorry. Oh no, I did do that wrong. 50 divided by 500. So, oh my goodness. I'll get it. So I might be, I'm 10% off. But 150 divided by 4,500, now I'm only 3% off. So the total distance I am will be bigger, but the percentage will be smaller. So when I convert that into averages, I simply divided this by 100, and I divided this by the square root, or sorry, I divide that also by 100. So if I divide this by 900, I'm going to get 5 plus or minus 150 divided by 900 is, oh wait, I need to divide that by, sorry, I need to divide it by 3. No, that should be right. 0.16, there we go. That is right. So this has a window of 1/2 on either side, and this has a window of 1/6 on either side. So the more draws you do, The bigger your chance error, but the smaller your percent error, which is what this box is saying. When drawing at random with replacement from a box of tickets, multiplying the number of draws by a factor of 4 divides the SE for the average of the draws by the square root of that factor. So if you multiply your draws by 25, you only have to multiply your error by 5, which is the square root of 25. So the number of draws grows faster than the percent error. Okay. Okay, next paragraph. As the number of draws goes up, the SE for the sum gets bigger, and the SE for the average gets smaller. Here's the reason. The SE for the sum goes up, but only by the square root of the number of draws. As a result, when the SE for the sum gets bigger in absolute terms compared to the number of draws, it gets smaller, which is what I just said. The division by the number of draws makes the SE for the average go down, and keep this difference in mind between the two SEs in mind. So we have SE for number, and we have SE for percentage and average, which end up being exactly the same thing. So the SE for number will go up, but the SE for percentage will go down. Okay, so that leads you to A. Let's do another set. 2. In section 1, the numbers in the box were known, and the problem was to say something about the average of the draws. This section reasons in the opposite and more practical direction. A random sample is taken from a box of unknown composition, and the problem is to estimate the average of the box. So just like we did with percentages, we are going to be drawing from an unknown box. We don't know what's in there. We don't know how many people are in there. But every person that comes out has a number, and we're going to take the average of all of the numbers. Okay? So how do we do that? Just like we did before. So along the way, there will be 2 questions to answer. Bullet number 1, what's the difference between the SD of the sample and the SE of the sample average? And 2, why is it okay to use the normal curve in figuring confidence intervals? Suppose that a city manager wants to know the average income of 25,000 families living in his town. He hires a survey organization to take a simple random sample of 1,000 families. The total income of the 1,000 families turns out to be $62 million. Their average income is $62,000. So I run around, I talk to 1,000 people, and I get an average of 62,400, it rounded. Okay. So the average income for all 25,000 families is estimated at 62,000. My best guess is that the true average that's inside this box is 62,400, plus or minus some amount. Okay. Of course, this estimate is off by chance error. The problem is to put a give or take number on the estimate. The SE is needed, and for that, a box model. So what I want to do is calculate the SE average. In order to do that, I need the SD of the box, and I need to divide it by the square root of 1,000. But there's a problem. I have no idea what's in the box, so I don't know what the standard deviation of the box is. What's the solution? Well, what was the solution before? We just pretended that the standard deviation we got from the sample was the standard deviation that was in the box. Okay, so the SE is needed, and for that box model, there should be 1 ticket in the box for each family in the town, showing the family's income. The data are like 1,000 draws from the box. The average income of the sample families is like the average of the draws, which we have. The SE for the average of draws can now be found by the method of section 1. The first step, is to find the SE for the sum of the draws. Since 1,000 is such a small fraction of 25,000, there is no real difference between drawing with and without replacement. So as long as there are a lot of people in the box, thousands and thousands or more, and the number we draw is very small compared to the size of the box, we don't worry about talking to the same person twice, because it's not likely to happen, and even if it does, it's not going to mess the average up. So 1,000 is very small compared to 25,000, so we're just going to pretend that we were drawing without replacement. Okay? So the SE for the sum is, well, anyway, they're gonna do it the long way. The square root of 1,000 times the SD of the box. Of course, the survey organization does not know the SD of the box, but they can estimate it by the SD of the sample. So in that box it says, with a simple random sample, the SD of the sample can be used to estimate the SD of the box. The estimate is good when the sample is large. How big is large? 625 or more, right? There's not a hard set number, but 625 is usually enough. So there are 1,000 families. The SD of their income turns out to be 53,000. So we're going to skip their method because it's slower. We are going to take 53,000 and do what to it? Divide it by the square root of 1,000. So 53,000 divided by the square root of 1,000. I'll throw another 0 in there. And I get 1676. Is that a confidence interval? Yes. Right. The first time we did this, it was not a confidence interval because we were inferring what would happen if we drew from a box that we knew. So we were guessing what will happen when we draw from this box. That's probability. Confidence intervals say we have drawn from an unknown box. We're going to guess what's in there. So I am 68% confident that the true average income in this town is somewhere in that window. And that cannot be described as a probability, because I'm either right or I'm wrong. There's no way to know which is which, but I'm one or the other. So I say I am 68% confident. I don't say there's a 68% chance, because the chance is either 1 or 0. Okay? All right. In the middle of the page, keep the interpretation of this $1,700 in mind. It is the margin of error for the estimate. So one point is worth discussing. The expected value of the sum of the draws is 100 times the average of the box. This is unknown because the average of the box is unknown. The total income of the 1,000 samples turned out to be $62 million. This is an observed value, and the SE for the sum was 1.7 million, measures the likely size of the difference between 62 million and the expected value. So the sum of all those people ended up being 62 million, give or take 1.7 million. Well, that doesn't do us a lot of good. We don't want to know what the sum of 1,000 draws is. We want to know the average. The 62 million doesn't really tell us anything. All right. So if we wanted to do a 95% confidence interval, we would times 1,700 by 2. Look at the top of page 417. That gives us a 95% confidence interval of 59,000 to 65,800. We're 95% confident that the true average is somewhere in there. Two different numbers came up in the calculations. The SD of the sample was 53,000 and the SE for the sample average was 1,700. These two numbers do different things. The SD tells how far family incomes are from the average, and the SE tells how far sample averages are from the population. Okay, so let's do that again. Example 3. So in example 3, we're drawing from an unknown box. And when we do that with a sample size of 400, so D equals 400, we end up with a sample average of total years of schooling at 11.6 and an SD of 4.1. So I want to create a 95% confidence interval. Well, I just read two sections to you to teach you to do exactly what we did in chapter 21. The idea is slightly different because we're doing average instead of percentage, but the calculation is identical. The formulas use exactly the same numbers. So all we have to do is 11.6 plus or minus 4.1 divided by the square root of 400, which is 20. So 11.6 plus 4.1 divided by 20. Yeah, that's right. And then and then 11.6 minus 4.1 divided by 20. And I am 95% confident that the true average is somewhere between 11.4 and 11.8. Wait, that's not what they got. Oh, oops. Yeah, this is a 68% confidence interval. So, so I need to put a 2 right here. And that gives me 11.2. Then I do the same thing with the plus. And then I end up with 12. Okay. Do we want to read this? Yes. So at the top of 418, that is the answer. The confidence level of 95% is the area under the normal curve between -2 and 2. Why is the curve relevant? Why can I use the normal curve? Because the incomes inside the box are probably not normally distributed. Income never seems to be. So why do I use chapter 5 when the box itself is not normal? Why am I allowed to use that? No, has something to do with my sampling method. So I talked to 400 people. If you talk to enough people, it will work. So this gives a computer simulation. So you can see the education level of the town in years. So we have some kids in lower elementary school, middle school, high school. And why is there a huge spike at 12? If I went and talked to everybody in Castledale right now, why is there a huge... Oh, and I'm only talking to people who are 25 and older. Most people graduated high school, okay? Some of them went on. It looks like about half of them went on to some college. Why is there almost nobody between 0 and 12? Most people 25 and older graduated from high school. So there are only a few that didn't. Now that box is not normal. So the sample is not normal. but the average of the sample with enough draws can be estimated by a normal curve. So if everybody goes out and talks to 400 people, then all of our results will look like the histogram at the bottom of page 419. So the box is not normal, but making multiple 400 draw sample sets will be normal. Okay. Need to work on A and B.